Good afternoon. It is calc time with Miss Wesley. So happy to be here again. Today's topic is going to be continuing to use integrals to find area between curves. And if we look at problems that we saw earlier in the unit, we used to have functions that bound a shaded region from the top and or the bottom, and we were trying to find the area in between. Well, today, what happens if we turn this picture on its side, and in something like this that you see at the top of page 8 of the area between curves packet, I couldn't necessarily classify this sideways parabola nor this function as a top nor a bottom relation, but this one, let me call this the left side of the bounded region. This should be your left function. Really, it's a relation, it's not a function. This should be your right. I could put function in quotation marks if I want to too. So the good news is it works very similarly to the other problems that we've already covered. While you're getting your notes ready up here on page 8 of the area between curves packet, I'd like to start with a joke. And speaking of math, what is a bird's favorite area of mathematics? Never forget, it's going to be algebra. Let's look at what this says so we can solve some of these example problems. Now I notice I have a right and a left side of this bounded region. I also make note that y is really important in this calculation. We used to be integrating from, say, like an x equals a to an x equals b. We had a top and a bottom function. Now we're going between two y values, c and d. So I notice that both of these limits of integration are y values in these sideways problems instead of x values. I also notice that both of the functions are kind of solved for x in terms of y. You're going to have, we'll call this a right side of the bounded region. If you want to, you could put function FCN in quotation marks minus a left function, right, instead of top minus bottom. A way I remember this is I think, well, it's the function that's more to the positive side of the region, right, the right, and then it's minus the function that bounds the region from the more negative side, the part that's to the left. And everything, this dy indicates everything in this calculation is done in terms of y. So I notice when I look at these examples down page 8, that I see y squared in some of these examples. I'm going to expect some sideways parabolas. And if they're not already, I would take both equations off the bat, solve them for x. So maybe just adding a 1 here, get a y plus 1 equals x for one side of this bounded region, and you get a y squared minus 6 equals 2x, and we can divide everything individually by 2. So y squared over 2 minus 6 over 2, so a 3 equals x. Our two functions. Now, even just looking back at how they originally appeared, what I think I might do is ignore the set of coordinate axes here and just graph my own little rough sketch of this. I notice y equals x minus 1 isn't too tough to sketch. It slopes up, it's shifted down 1 unit. And then think about what you would expect this to look like. Y squared equals 2x plus 6. Should open some kind of sideways instead of up or down because y is squared. And I don't see any negative leading coefficient. This should open the positive way. So if I wanted to guess what this would look like, I get a picture like this. And I care about the area of this bounded region in here. And what do we need? We need these two specific y values if we're going to set up this integral. We need limits of integration. Now, one good thing is you've got technology on your side to help you out. So I kind of went in to check these answers. I clicked on intersection points on Desmos for these two relations, and I got these 2 points, the point 54 and the point -1, -2. Which number matters more? We need the y value where these two functions intersect each other. So I need -4, I believe, was the first y, or -2 was the first y value, and +4 was the one over to the other side. Now, and I'll put y equals here as well. Now, just so that we know that we can do this, you do not need technology to get those intersection points. I do think it's important to show this to get intersection points. Intersection points. Don't forget that you can use substitution here. If both of these underlined equations are solved for x, we should be able to set the two expressions equal to one another to get these, to confirm these y values of -2 and 4. So a little bit of algebra should help me solve y plus 1 equals y squared over 2 minus 3. So just checking. Maybe I want to double everything right now to get rid of that fraction and get 2y plus 2 equals y squared minus 6 if that gets doubled. And then we can get everything to one side. 0 equals y squared minus 2y. And then minus 6 minus another 2 gives you -8. And then a quick factoring, y and y. With a 4 and a 2, as suspected, minus 4 and then plus 2 gives you two y values at the points of intersection. So just as Desmos had told us, y equals 4 is one of them, y equals negative 2. So either way, if you want to show the work for that or if you want to just use technology, that's fine. Now, the big part, let's set up the integral. So this is a sideways bounded region. We need to integrate right function minus left function, using the term function loosely. So area equals, we'll do integral from between two y values, from y equals negative 2 to y equals 4. What bounds the region from the right should be this line we see. So it should be x equals y plus 1. We're writing this in terms of y. Minus right function. So this is your left. And then in a second, maybe we put this in parentheses, the right equation. So this is x equals y squared over 2 minus 3. That's sideways parabola. And this is your setup. We've done most of the hard work. This is your left minus right side of that bounded region. We just want to simplify from here, take an integral, and then plug in negative 2 and 4. So then finishing things off, feel free to pause the video here and try it on your own, and then we can meet up, see if we match up. Let's simplify a little bit. So combine some like terms. I'll have negative y squared over 2 plus y, and then it looks like 1 minus negative 3. So we'll have a plus 4 at the end of it, dy. So we will take an integral. Area equals, let's take this up a power, negative y cubed over 2, but then over 3, so divided by 6. Plus y squared over 2, and then plus 4y. You are going to plug in plug in 4, subtract what you get when you plug in negative 2. So 4 goes first, negative 4 cubed over 6, plus 4 squared over 2, plus 4 times 4. Do not feel like you have to be taking this part of the problem as quickly as I'm going in the video. I'm just trying to save a little time, but feel free to pause. And then being very careful with the negative 2, so minus negative 2 cubed gives you 8 over 6, so plus 8 sixths minus a negative. Plus negative 2 squared over 2, so 4 halves is plus a 2. And then plus 4 times negative 2 gives you minus 8. If you take your time, simplify all that, should come out to be 18 square units for that area in question. Okay, let's try another. So this one, same kind of deal. You've got a sideways parabola, very common for these, and then the equation of a line. If anything's not already solved for x, we want to do it. So the first one looks like it is. For the second one, maybe I just want to move the 2y to the other side of the equation. So we've got this, maybe I'll box it, and we've got that. Then you can feel free to use the graph paper, use Desmos if you want to. Ignoring the graph paper though, I just want a sideways parabola again. We'll have x equals y squared. And then you have a line that I know, if you did solve this out and get the slope, it would slope up. It would have a slope of a half. So you're going to have a line. This looks a lot like the last region. This is x equals 2y plus 3. So this this or a calculator would just help me sort out which function's bounding the region from the right and which relation's bounding the region from the left. I can tell it's the curve on the left. We need two y values. We can either go in and use Desmos or use a graphing calculator or set these two expressions equal to one another and solve by hand. So you get y squared equals 2y plus 3. And this is just for intersection points. And this will be good because it'll give us the y values that we need. Move everything to one side, y squared minus 2y minus 3, and factor. Two numbers multiply to make negative 3, add to make negative 2. So 3 and 1 minus and plus. So calculator should confirm, or Desmos should confirm, that you get y equals 3 and y equals negative 1 as two y coordinates at points of intersection. So negative 1 all the way up to 3. That should help with the setup, right? Let's integrate from bottom to top. So from negative 1 up to 3 for this area. We want the right side of the bounded region, so 2y plus 3, minus the left side of the bounded region. So right minus left looks like y squared. We'll put a left there. And your setup is complete. We're going to integrate this whole thing in terms of y. I could reorder everything. If I'm feeling lazy, I'll just leave it in this order and take an integral of each term, because it doesn't look like we have like terms to combine. So take your time, feel free to pause here and work at this on your own pace. we can do 2y's antiderivative, so y squared, and then the 2 over 2 should cancel, plus 3y for the integral of 3, and then minus y cubed over 3. Not too bad. And then I guess I should have just ditched the integration sign because we're now taking an integral, and now we want to evaluate this from -1 to 3. So here goes. 3 gets plugged in first. 3 squared plus 3 times 3 minus 3 cubed over 3. And then let's subtract the rest in parentheses. -1 squared plus 3 times -1, and then minus -1/3. Maybe that should just be a plus 1/3 inside of those parentheses. And then we simplify. 9 plus 9, so 18 minus, speaking of 9, minus 9 again, minus 1, how about plus 3, and then minus 1/3. All said and done, you can check the solution. You get 30, whoops, kind of sloppy here, but you get 32/3 square units for that area. Okay, one more just to set up and give this a try, and then there'll be some for you to practice. F of y is 3 minus y squared. That's like saying x equals 3 minus y squared if you see an equation given that way. And then this is also like saying x equals y plus 1. So they did us that favor in this one of already solving these two equations for x and getting them in terms of y. Intersection points. I'm going to do like I did earlier, so feel free to either use technology or set these two parts equal. So intersection points. 3 minus y squared needs to equal y plus 1. And we pick a side. For everything, let's pick the right. And we'll say y squared on the right plus y, and then 1 minus 3 minus 2. We get 2 intersection points. So a 2 and a 1 should do the trick. Maybe if we make the 2 positive in the factoring and the 1 negative, that should do it. So you get intersection points y equals -2 and y equals 1. So we want at least a rough picture of what these two equations would give us in terms of a graph. I know one of them is linear and it slopes up. The other is a sideways parabola, but a calculator will show you that this time it opens in the negative direction. I see that negative in front of the x squared, so it's going to open to the left instead of the right. That should switch what our left and our right equations are. So we found this is going to be integrated from y equals -2 to y equals 1. And I think that's all there is to the setup of this problem. We want area to equal an integral. Pick the two y values, so it goes from -2 to 1. We want the right side of this to be the 3 minus y squared, it looks like from the picture. And the left side, subtracting in parentheses, y plus 1, integrated with respect to y. We'll simplify. So take your time with this. Feel free to pause the video. This is the integral from -2 to 1. This is, let's get this in order, -y squared minus y. And then here comes the negative distributed. 3 minus 1 gives you plus 2. Okay, we're on the home stretch. We take an integral, and then let's solve this. -y cubed over 3 minus y squared over 2, and then plus 2y. Evaluated at these two and subtracted, right? 1 gets plugged in first, so -1/3 minus 1/2 plus 2. And then -2 gets plugged in. Got to be careful with the negatives. So minus -2 cubed, so positive 8/3, minus -2 squared over 2, so minus 4/2 should just be a -2, and then plus 2 times -2 gives you a -4. Take your time, combine the like terms.